goes from a healthy air is yellow when it activates the effector pathways to get ready to design. We noticed that that was, of course, dose responsive over the domain, all of which is well above the biologically relevant range of the amount of nanograms per mil, but that also it was extremely variable from one cell to the next. So if you simply look at the accumulation of cleaved path-phase products in single cells, here you can see one example of a cell dying going to be alive. If you plated at this point, experiments suggest that these cells are really fully capable of re-entering a proliferative cycle. By this point, 14 minutes later, they're almost certainly dead. And if you then follow the activation of those pathways, what you see is a series of trajectories where there are, I've flagged one as early, middle, and late entirely on an arbitrary basis, and then you'll see later these are all small cell populations. But if you align these trajectories by the time of the mitochondrial outer membrane permeabilization by Mach, then you see what is really a completely stereotypical trajectory, namely that those pathways are off for a long time, and then bang, they suddenly turn on within about 10 minutes or so. And the duration of this delay, this is at a high dose of Mach, in typical concentrations we now use 2 nanograms per mil, even in the absence of ongoing transcription, this delay can be greater than 24 hours. So there's a long waiting process before you decide to die. And so we can sort of characterize that by the following simple figure to say that there's some sort of a delay period that individual cells have. There's some sort of time it takes from the pathway to the first action until the cell's actually dead. We call that TS switching. And then there's some overall efficiency of the process. And I won't have time to show you that, in fact, although you would think all cells are alive and dead, we've in fact identified cells in which by RNAi-mediated inhibition or by bortezomib treatment, you can take them halfway. We call those living dead. And the living dead have the unfortunate property of having scrambled their genome. And those are cells which actually don't take the process. I'm happy to talk to you about that. So if you now take these two parameters, the delay time and the switching time, the first thing you observe is that this delay, in addition to being dose-dependent, and that gives you the dose-dependent behavior, is really very different from one cell type to the next, and it's very sensitive on the other members of the destiny ligand receptor. In contrast, the time that it takes from the first manifestations of death to the point where you no longer can give rise to a viable cell are almost completely constant. And this is constant across almost all cell types we've examined, and constant across dose and ligand types. And in this case, it's on the order of 50 minutes, and if anything, we think this is an overestimate of that. The second thing to tell you about this pathway is if you actually look carefully at the dynamics of the upstream process, you see something completely different than what I showed you downstream. In this case, you see the same variability, and I've tagged an early, middle, and late. But if you superimpose those trajectories, in this case, you see the canonical behavior that immediately after ligand has been added to those cells, that they now activate the upstream part of the pathway, and they hold the downstream part entirely. And it turns out this is a very difficult piece of biochemistry for the cell to arrange, because the immediate target of the upstream path phases are in fact the downstream path phases that will go on and kill you. And so, strangely, a cell, not yet committed to death, is creating tens of thousands of molecules of a potent enzyme fully sufficient to kill it, but it's holding that activity. Now, one of the problems of any kind of sort of live cell analysis of this is that you really have to worry that what we had observed here of biosensors is really not typical of the natural substrate. And so one thing within a kind of sort of quantitative framework that I'll tell you about in a moment, and I won't show you the data here, is that we always attempt to fuse as many different measurement methods as possible, and so the live cell imaging here is backed up by standard flow cytometry as well as by conventional biochemistry. And you will immediately realize that, of course, the average behavior of, say, 1,000 disks imaged in a cell is exactly what you would expect to see in the Western blot, and it's gratifying that you can show in a dose-responsive way that precisely the behavior we see here by imaging is what we see by flow and by blot. And this also allows me to point out one other aspect of the dynamics that we didn't appreciate until about 3 years ago. And that is that if you take a population of cells and you measure this entirely on a population average by doing a Western blot, you think that it takes the average cell on the order of 4 to 5 hours to activate it after it's done. But that's not true. It takes 10 minutes, just that the cells don't all do it at the same time. So this is one of many examples in which I think the single-cell analysis gives you a fundamentally different picture of the dynamics than you would get by doing biochemistry across. So the question we have to now ask ourselves is how in the world does this kind of what we now call a snap action variable delay switch, namely how does this work? Namely that the cells are able to wait for a very long period while accumulating clearly within them the potential to die because they've activated at least some of their caspases. They haven't committed to death, and then bang, in 10 minutes, after, let's say, a 24-hour death delay, you're going to make this. And here's where I want to tell you a little bit about how we're trying to think about dynamical systems of this type, biochemical systems, in a little bit more quantitative. And let's ask ourselves first, where would we start for any such analysis? And what we have are all these pictures, and we call these figure 7 pictures because they're always figure 7 when you submit your paper to Cell. Although in this particular example, the goal is to click through and order antibodies. We've got a large investment in the community in putting together interactomes, which are some sort of depiction of biochemistry in low resolution. And then at the same time, we have obviously these marvelous high-resolution structures here, exactly the way we will show you in a moment. And the question many people will ask, can we move directly from knowledge of high-resolution structure through these kind of pathways to the type of dynamics that we're doing today? And the answer is not yet. Now, why is this a hard problem? And I think when I go and talk to my friends like Todd Golub and I go in his lab and it looks something like this, I'm really reminded of the extraordinary computational infrastructure that we've built around modern genetics and genomics. And if you were to come to my laboratory and look at exactly the same setting, you would see it look something like this. So we, in fact, largely use reasoning about biochemical systems that's 100 years old. Michaelis-Menten blindly reversed. I mean, these are antiquated ideas for systems that are, in fact, much more complicated. And we recently, at some cost to our sanity, actually wrote a little paper, if anyone's interested in gene development, where we go in and directly address the comparison between the dynamical systems approach I'm going to show you today and the kind of classic Michaelis-Menten kinetics you may have learned. And what I'll tell you the bottom line is, one is a very special example of the other, and one which increasingly we think has little application to biology of natural cells. So how would an engineer think about this? And this was dating back now to Jim Anderson, who recognized this when we started our little systems biology center at MIT. Well, what engineers have is large, complicated problems, and they have underlying them schematics, universally drawn, so that any engineer can come along and figure out which pipe should be attached where. Of course, they know that because they engineered it that way. They can't discover it. And then critically underlying this is some sort of a mathematical representation. And the existence of that mathematical representation is very critical because it allows you to reason across ideas that are simply too complex for human intuition. Now, when we started out on our systems biology center, we imagined we could go across to the chemical engineers who are numerous at MIT, and we would find from them the exact tools we needed to think about, let's say, trail biology. And it turned out that that wasn't true. They had virtually nothing to share with us. And the last couple of years have actually been a process of trying to work out what sorts of